Hello, in today's video I'm going to be talking about oscillations. More specifically, I'm going to be looking at simple harmonic motion. I do want to note also that the problems I'm going to be referring to are part of a 3-series problem between number 33, 34, and 35, so I strongly recommend that you go watch those after this video. So, simple harmonic motion is what an object undergoes if the displacement is directly proportional to the linear restoring force. So essentially there are multiple formulas and ways to look at simple harmonic motion. First, I'm going to go ahead and draw a simple diagram that illustrates simple harmonic motion. So we've got circle here, and radius A. We've got theta here. Theta is that. And then I'm going to draw 4 axes. 2, 3, 4. Okay, so essentially here x is going to be equal to a cosine theta by basic trigonometry, and y is going to be equal to a sine theta. And then we know that the object or particle is moving in this direction with an angular velocity. Essentially, when an object is displaced, it may be subject to a restoring force, which results in a periodic oscillating motion, which could look something like this. Let's get M here, and x is equal to a at this point, x is equal to 0 here, and x is equal to a. Oh, sorry, this is negative a, by the way. And this is k. So that just gives kind of an overview of simple harmonic motion. Two key formulas that come out of this are x of t, position of t, is equal to a cosine of angular velocity times time. And the other one is simply x of t is equal to negative w a sine of the angular velocity times time. So now that we've got that established, we're going to go ahead and apply this concept to an example. So the question reads: an object is initially hanging in equilibrium from a vertical spring. The object is pulled down to 15 centimeters from its equilibrium position as illustrated above and released at time t equals 0. The object then oscillates with a period of 2.0 seconds. Let x equals 0 be the equilibrium position and let the positive direction be upward. So I'm going to go ahead and draw a quick representation of this diagram. Put a bar here, our spring, the object here, and then this is the representation of the spring, floor. We've got this is 15 centimeters. This is x equals 0 centimeters. Trickling down. And this is the positive direction. Okay, so problem number 3 specifically asks, what is the position of the object at t equals 3.0 seconds? We know t is equal to 3. So we can go ahead and use our formulas here and plug in to find what the position will be. So we know that the max displacement will be at 15 centimeters since the object is pulled down. Then we use the equations of motion, which is this. Also we know that the period is 2. So I'm going to go ahead and write that down. Period is equal to 2. Okay, so we can go ahead and plug into this formula, and we get x of t is equal to 15 times cosine of 2 pi, the period, over 2 times 3, which is equal to negative 15 cosine of 3 pi. Cosine of 3 pi is equal to negative 1, so this is going to be equal negative 15 times negative 1, which is equal to 15 centimeters. This is our final answer, and it is equivalent to option A on the exam. Thank you.